Okay, so I think that's the end of the emitter follower. I'm going to double check here. What's the next slide? Okay. So now the next thing after the emitter follower is the current source. So now I'm going to help you out a little bit. He wants you to observe the behavior of the current as a function of the load resistance. And I have the variable resistors over there. I'll hand them out. I'll show them to you. And he wants you to explain what you see by quoting rule number 1 and rule number 2. And then, of course, IC equals to IE or IC equals to beta IB. And, of course, the first two conditions, VC and VE, and VB and VE. So to help you down that road, I will tell you is, what is VB? What will voltage at B be, if you forgive me? Notice that's a fixed voltage, not a sine wave. We've gone over this a little bit. So what will be the voltage at the base? And then try to measure it. Then what is the I emitter, which basically is I collector? And then vary the load resistor back and forth from 0 to 10K, or depending on, maybe you need to use a 20K. We may not have enough 10Ks. And notice the behavior of the current. You can also monitor the behavior of the voltage at the collector. And you might read the paragraph again that he has there. So things are going to stay the same or things are going to change. And we'd like you to explain what's going on. You might even just make a simple table. I turn the resistor and I notice that the voltage is this, the current is that. I turn the resistor some more and I see this, I see that. Now you have to figure out, turning it left is towards 0 or is turning it right towards 0. So you'll need to test it. You know, you have an ohmmeter, you have your handhelds or ohmmeter mode, or you do your plug-in voltmeter. I'll tell you that when you look at the little resistor that you're going to get, it's a 3-terminal device. It's got a square, a blue square with a white knob, and you put a screwdriver into it to turn it around. And so the two outer terminals, these 1 and 2, are the outer terminals. And then number 3 is the middle terminal, and that's the variable one. So when you use this, notice the way they have it hooked up here. They're using terminals 1 and 3. So you're using 1 and 3 or 2 and 3. Oh, and FYI, when you look at the terminals coming out of this thing, for some reason they're shaped like an S. You have to take your needle nose and straighten them out so they'll go into the breadboard. The potentiometer, that's this, and that's a potentiometer terminal. You may have some sitting in front of you already if you have one of the daily pill boxes from previous semesters. I would test them to see what they're, you can quickly test them by measuring the resistance across 1 and 2. So you want R12 to be about 10K if possible, but you need some either that or greater than or equal to 10K. If you have less than 10K, you won't observe all the behaviors. But if you use 100K, it'll happen so fast that turning the knob, the behaviors will happen so fast it won't be any fun either. So something like 10 to 20. I know we have 10, and I know we have 20, and maybe we have 15. But we'll take a look. I have them over there. The two, oh, I'm sorry, I didn't label them. 1, 2, 3. Yeah, I should have put a picture of one of them in there. Sorry. It's easy enough to do. But, you can always just say, yo, H, what do I do with this stupid thing? And remember, little screwdrivers are floating around. There's some on the table. I'm sure there's some floating around the room. Okay, what's next? Okay. So now we have two things going on to take away from this illustration. The blocking capacitor and the biasing. So we'll go over the biasing first. So if I have a voltage divider, right? I told you we'll never get away from voltage dividers. Of the 130K resistor and the 150K resistor. So we can see then the voltage at the base is going to equal of 150K, right? It's the lower resistor, divided by 150 plus 130 times 15K, and that equals about 8 volts, which, by the way, is not halfway, because, of course, the output is going to be the input dropped by about 0.6 volts. So we need that the center output, the input has to be 0.6 volts above it. This is part of 4W1 and 4W2, right? So that's why I wanted you to look at and make notes. And then you see then that the 8 volts drops to about 7.5. And then, of course, now we have a 7.5K resistor. We can, just as a side note, our side note is then that IC is about 1 milliamp, which is the so-called quiescent current. But now what happens is the biasing network takes a signal. It's small, but you have a signal like this at 0 volts. And let's say this is 6 volts, and this is minus 6 volts. Now what it does is that 0 volts, 7.5 volts, and you can go negative And what you see in the outside, let's see, the outside world, yeah, you'll see it above 0. But you're not clipping the lower lobes. Now, of course, we have 6 volts and 6 volts. At some point, you can't go more than the rails. And in fact, for us, we're going to have plus 12 and ground. So in fact, we wouldn't be able to reproduce 6 volts. So let's say that's 5 volts. But in this case, we're reproducing. In fact, I should just keep this the way it was. In this case, we're going to move the baseline up by about 7.5 volts. And now we can see negative swings, even though we don't have a negative supply. So now also in this case, since we don't want the source to affect our bias, and if it draws current away, or it can affect the bias in a couple different ways, what we want now is that we don't want the biasing network and the source to interact. So once again, we put a blocking capacitor. Notice this one is 1 microfarad, and you hopefully recall from 4W1 and 4W2, there's formulas for calculating that. Because really, we very rarely care about DC levels and amplifying DC levels. We're much more interested in amplifying things that wiggle, either randomly or not unpredictably, at least initially unpredictably, or of course in a predictable manner, like a sine wave, or like meaning a song or a voice or something like that. So now the next thing that you're asked to do is to build this common emitter amp. So to help you through it, I'm asking you to calculate the voltage at the base, which is basically the voltage divider. Then you can calculate what's the I emitter. And it says calculate V out. Well, in this case, let me think about this, because I'm realizing now that this thing is quiescent. Oh, yeah. What's V out when I have no input? So I didn't make a mistake. And then he says what's the Z out? And if you did those notes I asked you, you can actually calculate both. The input and output impedance you can calculate. So I want to see you make a try at that. And of course, measure it. You can also calculate the gain. So you can calculate it, and you can measure it. And of course, this is with a sine wave. And the last thing, I don't know if you'll get to it today, but it's the last thing before the transistor switch. They want you to add this capacitor. And not to take you too far down the road, just to get your brains thinking, remember once again that the gain is the resistance, the collector resistance, divided by the emitter resistance. But now, the emitter resistor is the 750, 150, not K. Oh. In parallel with the capacitor, which has a resistance of 1 over 2 pi Fc. And so I want you to think about gain, basically rule of thumb for parallel circuits, and gain as a function of frequency. Now, he's telling you to give it a sawtooth. And you should observe this so-called barn door effect. So there's a discontinuity here, but you see that the gain sort of tapers off a little bit. It's a bear to describe, and I will see if I can, but let's wait and see if you get that far. Certainly on Thursday I'll talk about it and the transistor switch, and on Thursday I'll go over the two examples a little bit, because that's going to segue us into chapter 5. Okay. I'm assuming questions would have been asked, or maybe you're just so glazed over now you can't think of a question. But you know where I am. So I'll stop this and I'll get it posted up.